So, working on the work, power and energy, in the last lecture, in the last class, we talked about many aspects of potential energy and kinetic energy, etc. Okay. Now, I wish today to state explicitly as to how the conservation of mechanical energy takes place. Conserved means the energy remains constant, remains unchanged. So we see that the way we have defined things, the delta kinetic energy turns out to be equal to Fx into delta x, where delta x is the displacement that has taken place under a force Fx. You will see that this force has to be a conservative force. Also, I established for you about the potential energy in the case of gravitation and also in the case of springs, but which today I shall elaborate further. And we found that a relation exists, that minus of the delta change in the potential energy is also equal to Fx delta x. Okay. So these equations 1 and 2, if I subtract the second equation from the first equation, then what I find, delta k minus delta v, which is plus delta v, and this turns out to be equal to 0, because on the right hand side we have the same quantities. So I can write the delta k plus v is equal to 0, where k is the kinetic energy and v is the potential energy of the system. The change in the kinetic plus potential energy of the system at all instants of time in all situations is equal to 0, which I can write elaborately for 2 points I and j, okay, in the system. Then I can say the kinetic energy at the situation I, where the value of x is xi, plus the potential energy Vxi is equal to kj plus Vxj. Okay, so this is an important relationship that we obtain, that the sum of the kinetic and potential energy of the system is constant, or change in the sum of the kinetic and potential energy of the system is equal to 0. Now from there we arrive at the following, some of the definitions associated with the conservative forces. The first forces which we define conservative and from where we take our leads. Okay, so one of the things is that Fx is conservative if it is derived from a scalar Vx. Interestingly, this turns out to be equal to Fx is equal to minus ddx of v, the potential energy of the system. So this is one of the definitions, that the force, the conservative force, is derived from the scalar Vx by taking the spatial space related. We are talking about one dimension because it's easiest to talk about one dimension, else we could talk many dimensions, I mean x, y, z, etc., etc. So Fx is equal to minus dv dx. This is one of the things which is an important part of the conservative forces. Second, the work done by a conservative force depends only on the end points. For example, here I write that W is equal to Kf minus Ki. Well, here I just want to tell you one thing, that my W is positive if Kf is greater than Ki. Okay, and W is negative if Ki in magnitude is greater than Kf, or Kf is smaller than Ki. Anyway, that defines the positive and negative work done. According to this relation we call the work energy relationship. So Kf minus Ki, this I will get as, when we deal with the potential energy of system, this will turn out to be equal to Vxi minus Vxm. Xi the initial value and Xf the final value. Then the work done by a conservative force over a closed path is equal to 0, because the final position becomes equal to the initial position. Initial position becomes the final position. It is from final to final, or initial to initial, any intermediate point to the same intermediate point over a cycle. Those students who are versed with E dot dr, the concept of E dot dr in the system of electrostatic forces, they know that the E dot dr over a closed cycle is equal to 0 as this thing. So in a similar way, there also E dot dr is equal to 0, because the force derived from the field, that is also, in the case of electrical systems, it is also a conservative force. So we have to be clear about what kind of conservative forces we are talking. Now here, therefore, after this much discussion, I can say that the total mechanical energy of a system is conserved. Total mechanical energy of a system is conserved if the forces acting on the system are conservative forces. The total mechanical energy of a system is conserved if the forces acting in the system are conservative. Conversely, we can say if the forces acting in the system are conservative, the total mechanical energy of the system is conserved. Okay? May I repeat it? Please listen carefully. The total mechanical energy of a system is conserved if the forces acting in the system are conservative. Forces are conservative. And conversely, I can say if the forces acting on the system are conservative, the total mechanical energy of that system is conserved. We need illustrations. And I'll give you illustrations by two examples. One, employing the gravitational force. I'll take up the case again of the ball falling freely under gravity, and then another spring force, for which I have already derived the values of the potential energy mg, h and half kx square under the various situations. So I'll deal with that. So the first case of studying the conservative force, which is the gravitational force, is a very simple example I'm going to take first, and that is I'm going to examine as to what happens when a ball or a body is allowed to fall freely under gravity. Now we understand that if we take the potential energy of the system over here equal to 0, then the kinetic energy of the system will be 0 over here, which is evident from half mv square, or v square is equal to 0. In between it has got some value which is associated with the height h, and there is a final value which is the maximum kinetic energy when the potential energy of the system is equal to 0. So I am trying to write the equations for EH, E small h and E0. EH at the height capital H, at the top of the flight down the vertical line, EH is equal to mg capital H. which is basically its potential energy, because kinetic energy which is associated right now is equal to 0, so EH is like this. At this instant of time I can write, because the potential energy is equal to 0, the entire energy is kinetic, and therefore it is half mvf square. Okay. In between, it has a potential energy component mg associated with the height small h that we have, and half mvh square, which of course is greater than the velocity over here and smaller than the velocity over here. So this is the conservation of potential energy plus kinetic energy for a falling body examined under the spatially, this word comes from space, but when we write spatially we just remove that c and put in t over here, so it is spatially independent force Fx. Now the mechanical energy is conserved as it should be, then the energy EH should be equal to the energy 0, and that I am writing over here. mgh is equal to half mvf square, which ultimately gives Vf is equal to under root 2gh. This is the result that was obtained by us before too. In the second case, when we equate the total mechanical energy over here mgh to the total mechanical energy of the system under the conservative force mgh plus half mvh square, if I write this equation here and then I solve it, then I find that the velocity at the height h squared turns out to be equal to 2gh minus h, where h minus h is this height, and of course the velocity at the top has been taken as equal to 0, so it is nothing but the manifest of the kinematical equation, the third equation in kinematics, v square is equal to u square plus 2as. Okay. Now next we take the case of very interesting situation, and that is called the motion of body in a vertical circle and disconnected with a string, and we have to see if what is the condition that the body can go in a vertical circle. What should be the minimum possible velocity at the top and associated velocity at the bottom, and how can we calculate the various velocities there with the law of conservation of energy situation in the next problem that we take up. Now this is an interesting situation where I have a mass m tied to a string, massless string, inextensible string, and it can move if it is in a short this thing, then it can be, say, like one extreme position could be this and the other extreme position could be this, and at the same height on the left hand side, on the same height to the right hand side, and here the potential energy of this ball is taken as maximum corresponding to the height whatever over here is small h or whatever, and the pendulum goes to and fro, in the meantime reaching the equilibrium condition, the equilibrium position of the ball under motion, and what results is the physics of a simple pendulum. We'll see it later on. Okay. Now what this circle is a vertical circle. If I increase the velocity over here, which is taken as v naught, then of course it rises up and up because the energy associated over here is half mv0 square. Okay. Now what happens is that this goes up and up and up, and maybe a motion of this kind, a perpetual motion of this kind takes place. Now there are two kinds of forces, two external forces which are acting in the system, and the system consists of, this is again a case of conservative forces. So one of the forces which is acting over here is due to gravitation, due to the gravitational field mg, and the other is the tension in the string. And tension I explained out to you. For example, tension over here is in upward direction, TA, and TC is taken in the downward direction. Okay. So we are interested in knowing as to what is the condition that this motion occurs uninterrupted. That is, we want to know as to what is the minimum velocity that this Vc should be. The minimum velocity Vc has, that depends upon the velocity that is here, and the velocity of course here will be equal to Vb, like that. I'm not showing it right now. So in this case of a very interesting motion in a vertical circle, this is the minimum velocity that we are going to take, because the minimum velocity will be obtained when the tension in the string is equal to 0. That means the entire centripetal force in that case is provided to it by mg, and here the centripetal force is provided by the tension in the string minus mg. That is the force which is center seeking. Okay. So let me be clear, let us be clear that no work will be done by the tensional force. No work will be done by T, as tension in all situations you can see is perpendicular to the velocity vector. As therefore the tension dot velocity will be equal to 0, and this occurs when there is an angle of 90 degrees between the two of them, which is the situation here, here, and at all points, because the velocity is tangential and the tension is radial. Okay. Tb is also shown to be towards the center, Ta is towards the center, and Tc is towards the center in all these situations. So what I am going to find out as to what is the value of the velocity V0 such that the velocity over here is such that this motion occurs. Okay, the minimum velocity over there. The velocity at this point, which is just taking a point at a height of L from the bottom, okay, because this will be equal to this, and that is the difference, and also what is the value of Vc, and then we can calculate as to what is the ratio of the kinetic energy over here to the kinetic energy at the top. And similarly Kb and Ka, etc., etc., all kinds of calculations can be done. So what we see is that the potential energy of the bob in this very interesting system which I have just described to you verbally, the potential energy of the bob is associated with the gravitational force only. Okay, so I can write, if I take at this point the potential energy of the system to be equal to 0, that means we are the associated kinetic energy and the associated velocity is maximum in this system. Then I can write for the position A here, I can write the equation that the total mechanical energy of the system is equal to that 0 potential energy plus half mv0 square, that is half mv0 square. And the second thing is that the tensional force over here minus the mg, the force that is there, and that is what is going to provide mv0 square upon L, which is nothing but the manifest of the second law. Okay. At Tc, at C, over here, we take the condition that Tc is equal to 0. That means the string just slacks, or there is no tension in the string, and the corresponding velocity of the bob or the body is equal to Vc. Okay, then I write this. I find that for entire mechanical energy I can write at C that this is equal to half mvc square plus mg into 2L. 2L why? Because L plus L, the diameter of this circle is equal to L plus L. Don't worry, if you want you can take capital R for it and you can derive your formula accordingly. So I get this, and then I write that the relation over here, this is mg, Tc is equal to 0. So mg is the total centripetal force, and this I can write that mg is equal to mvc square upon L. This is again like before, it is the manifest of the second law of motion, and therefore I can write, if I substitute, okay, if I substitute the value, then E here becomes equal to half mvc square plus mg I can write as vc square upon L and multiplied by 2L, L and cancels, so this becomes 2vc square, 2mvc square, and plus half mvc square gives us 5 by 2 mvc square, which I can write as what we obtained here. If we equate the energy, this energy to the energy at the point A, which is half mv0 square, so the result that we obtain 5 by 2 mgl, okay, from here I just get v0 square is equal to 5gl, and that gives the velocity at bottom to be equal to under root 5gl, which I have written over here. At the point B, midway between the two of them, I can have I can write the equation as half mvb square plus mgl, and equating to the energy, total energy at A, considering the conservation law, I can write this half mvb square plus mgl is equal to half mv0 square, and which gives ultimately that vb square is equal to 5gl minus 2gl, which is equal to 3gl, and from there I can write the value of vb as equal to under root 3gl. The value at the top we calculated already, it is gl, and then in the mid 3gl under root and 5gl under root, okay, this like this. Now I can calculate half mvb square, half mvc square, and then I find that half m and half m they cancel, and 3gl divided by gl, the ratio of the two becomes equal to 3:1. Now this was a very simple way of doing the things. We can make complications. What kind of complications we can do? We can define the position on this circle in terms of an angle theta, and then if we take this as L, then this becomes L sine of theta, then this as L cos of theta, etc., etc., and we can complicate the things and still with the help of these steps, with the conservation of mechanical energy that we have, we can do it. Interestingly, before I quit today, in a few moments time, I will ask you that suppose this is going on, the string is there, and when the string is at the point A and the string goes, snaps, what will happen to it? If it is still a certain height from the surface of the earth, then I will get a projectile motion, which in the hyperbolic situation that is there, from the top of this, I throw a projectile with the velocity v0 and etc. etc. What happens if the string snaps at this point? At this point the velocity is like this. So it will be just projected upwards, okay, and its motion will be described as the motion of free fall of a body, which is launched vertically upward direction with the velocity which corresponds to Vb, which is under root 3gl. Okay. What about here? Here also it will be projected like this in the horizontal direction. It will again take the projectile path, etc. etc. So these are the complications that we sometimes bring in, but for now what we have done today, I have done in two cases the conservative forces due to the gravitational system, and continued with that. Next time we will deal in detail the conservative forces due to the spring mass system, which I have explained partially to you. So I propose that you come prepared with that, and then we discuss the things one by one. So the conservative forces, as I define that, the conservative forces are one which arise out of and give conservative work done. So we'll talk more about that in the next outing. Thank you very much.